Hello all, welcome to the session on relational algebra. The overview of relational algebra. The basic set of operation for the relational model is the relational algebra. The relational algebra is very important for two reasons. First, it provides a mathematical foundation for relational model operation. Second, it is used as a basis for implementing and optimizing queries. The relational algebra is the basis for the structured query language. So we actually don't implement relational algebra. It is nothing but it's a collection of mathematical expressions. Unary relational operations are select operation, the notation used is sigma, project operation, the notation used is pi, and the rename operation, the notation used is row. The select operation is used to select the tuples or the rows from the relation, whereas project operation is used to select the columns or attributes from the relation. And whereas rename attributes, so rename operation, it is used to rename the attributes of a particular relation. Let us look into the select operation. The select operation is denoted by sigma, is used to choose a subset of tuples from a relation that satisfies a selection condition. So those tuples that satisfy the condition are selected, and those tuples that do not satisfy the condition are discarded. So that is based on the condition. So this is a syntax. The select operation is denoted by sigma, and then the subset selection condition, and within the bracket relation R, name of the relation. Let me consider a simple example. Let us select the employee tuple whose department number is 4. So here the relation name is employee and the condition is department is equal to 4. And here we are just selecting the rows. We are selecting the subset of the rows. So the expression looks like this. So we have employee and the condition is department is equal to 4, and the notation used is sigma, because I am just selecting the subset of rows. I am just selecting the rows, not column. Let us look into the one more query. Select the employee tuples whose salary is greater than 30,000. Now the relation name is employee and the condition is where salary should be greater than 30,000. Yes, the expression looks like this, where I have employee is a relation, condition is salary greater than 30,000, and the notation used is sigma. Yeah, let us consider one more simple example. Select the tuples of employees who either work in department 4 and make over 25,000 per year, or work in department 5 and make over 30,000. I repeat again. So we'll be using a table relation name called as employee. Here we have two conditions, that is either he need to belong to department 4 and make over salary greater than 25,000. Either he should be in a department 4 and salary should be greater than 25,000, or he should be in a department 5 and the salary should be greater than 30,000. So my expected output is somewhat like this. You can see here department 4 and salary should be greater than 25,000, and belongs to department number 5 and salary should be greater than 30,000. So let us my expression or my relational algebraic expression looks like this, where I have employee relation and within the two conditions. So department number is equal to 5 and salary should be greater than 30,000, or department number is equal to 4 and salary should be greater than 25,000. So here I have used a sigma operation, because what sigma does is it selects the subset of rows or tuples based on the condition. Okay. Next we'll look into the project operation. The project operation is denoted by pi. Let's see why project operation is used. The project operation selects certain columns from the table and discards the other column. Like in case of a select operation, it just selects the rows or tuples from the relation, but in case of a project operation, it selects certain columns from the table and discards the other column. Let us look into the some syntax of the project operation. Look at this. The project operation is denoted by pi, and then the attribute list. Here we don't specify the condition. Here we specify the attribute list, and then the relation R. Let me consider a simple query. List each employee's first and last name and salary. I want to list all employees' first name, last name, and then the salary, which means I'm selecting the columns. Yes, employee, last name, first name, and salary, and then the notation pi. So here we don't specify the condition, here we specify the attribute. So just the resultant output will be just consist of the last name, first name, and the salary. So rest of the columns will be discarded. One more query. Retrieve the first name, last name, and salary of all the employees. You look at this. This is my table. I want only the first name and the last name and the salary column. That's it. And the salary column. I want to discard rest all the columns. So yes, my output should look like the resultant output should be like this. So it should consist of only the last name, first name, and the salary. Yes, the relational algebraic expression used is employee, last name, first name, and the salary. So this is what pi operation does. The pi operation will be just selecting the columns, whereas select operation will be just selecting the rows. That's it. Yes. One more simple query. Retrieve the first name, last name, and salary of all employees who work in department number 5. Let us read the question once again. Here, retrieve the first name, last name, and the salary. I need first name, last name, and the salary. Yes, column could be selected by pi operation. And the condition, I have one more condition, that who work in department number 5. So the resultant algebraic expression is the combination of sigma and pi, because here I need to select the tuples, also I need to select the columns. Yes, so this is the employee table. Yeah, you can see here, from the employee table I need to select a particular row, that is I need to select those column with department 5 first. I need to select those rows belong to department 5. Yes, I selected this, some of the rows which belongs to department 5, and from that I need to select the columns, first name, last name, and salary. So my output, the resultant output, looks like this, where it retrieves the first name, last name, salary of all employees who work in department 5. Yes. One more example. Retrieve the first name, last name, and salary of all employees who work in department number 5. Yes, same problem, but with a different technique, giving a name to each intermediate relation. Yes, I can split the entire relation algebraic expression like this. You can see here, employee table. From an employee table, I will just select those rows who belongs to department number 5, and I name it as temp. So my output, the resultant output look like this. So here what I'm doing here is I'll be selecting only those employees who belongs to department number 5, and I named it as temp. You can see here I named that table as temp. Now what I have to do here is I need to select only the first name, last name, and the salary. Yes, from the temp I will be selecting first name, last name, and salary, and I will name it as R. So the resultant output is this. So with the table R, I just retrieved first name, last name, and the salary. So that's it about the select and pi operation. It's very simple. Either you can write it at a stretch, you can combine those select and project operation, or you can split it in this way. Split it and give any name, and again this will be the final resultant output. Now let's see how to rename the attribute. So renaming the attribute could be done by making use of a notation called as a row. Let me consider one more example, same example, where I retrieve those rows of all the employees who belongs to department number 5, and I will name that relation as temp. Yes, I named it as temp. Now, yes, now what I have to do here is I need to retrieve, yes, or as I said in the previous same problem, I need to retrieve the first name and the last name and the salary, and I need to make the resultant attribute as R1. Yes, I've done it. You see, from the temp I just retrieved first name, last name, salary and named it as temp. But now, instead of f name, I want to rename this f name as first name, and I want to rename this l name as last name. So that could be done by making use of a notation called as row. Look at here. We have R1 relation. From the R1 relation, making use of the notation or making use of the symbol row, I just modify the first name as first underscore name, last name l name as last underscore name, and I'll keep salary as it is. So the resultant relation looks like this. See, I can see here the attributes are modified. F name is modified as first underscore name, last name is modified as last underscore name, and salary is modified as salary. Yes. Let us understand about the set operations. First is union operations. Let R and S be the two relations. Here we have two examples of R and S. So let's see what union operation does. R union S is a set of all tuples belonging to either R or S or both. So in R union S, duplicates are automatically removed. You can see here in the relation R, I have 100, 200 and 300, and id and in relation yes, I have id with 100 and 400. Here you can see here, when I combine both R union yes, the ultimate resultant output will be the 100, 200, 300 and 400. There will be 4 rows, and the 100, this duplicate values will be removed automatically using this set operation. Set theory operations using intersect. So here are the two R and S. So intersect, what it does is, which is common here in both R and S. Yes, 100 is common. So the intersection is nothing but 100, only one row. Difference. R minus S is a set of tuples belonging to R and not to S. Okay, so which is available in R and not in S. So the data which is available in R and but not in S is 200 and 300. Yes, the resultant output is 200 and 300. Yes, let us look into the Cartesian product. The Cartesian product combines all possible combination of tuples from two or more relation in one single relation. So Cartesian product is denoted by cross x. So here what happens here is, if I perform a1 cross a2, all the rows will be combined with all the rows of a1 will be combined with all the rows of a2. Let's say like Anup a1 will be combined, so the first row of a1 will be combined with the first row of a2. Again, it will combine with all the rows of a1. Yes, let us understand about renaming of the attribute. The attributes can be renamed by making use of a notation row. And yes, this is a previous example where we select those tuples of employees who belongs to department number 5 and assign it to the relation temp. Now what I have to do is, I want to select those the columns, that is first name, last name and the salary. So yes, first name, last name, salary can be I've selected it. Now what I have to do here is, I want to modify the attribute name. I want to modify f name as first name, l name as last name. So yes, I want to do like this. So this could be done by making use of a notation called as row. Yes, look at this. This is how I select all the columns by making use of a pi operation, and I've stored, and the resultant relation is R1. And here from the R1, using the operation, using the notations row, I will be modifying those attributes to first underscore name, comma last underscore name, and then the salary. And I will be, the resultant relation is R. So this is my final resultant relation. Yes, in relational algebra I can modify the attribute name using the notation row. Let us understand about the set theory operations, union operation. Let R and S be the two relations, yes, and R union S is a set of all tuples belonging to either R or S or both. So in R union S, duplicates are automatically removed. You can see here the ID of R 100, 200 and 300, and in ID of S is 100 and 400. Here you can clearly see that 100 is a duplicate. So in the final resultant the union operation, you can see that the duplicate values are removed. So only we have is union, that is 100, 200, 300 and 400. Yes, let us understand about the intersect operations. Let us consider two relations, that is R and S. Yes, R intersect S is a set of all tuples belonging to both R and S. So the set of tuples belonging to both R and S is nothing but only one tuple with the ID 100. Next operation is difference operation. So in it is the notation is R minus S. So here, when here the duplicates are automatically removed, and yes, R minus S is set of all tuples belonging to R and not to S. Yes, the data which is available in R will not be in S. So let us see the ID which is available in R but not in S is only 200 and 300. The ID which is available in R and not in S, that is called as R minus S, is only 200 and 300. So the resultant output is to R minus S is this. Let us understand about the Cartesian product. The Cartesian product combines all possible combinations of tuples from two or more relations in one single relation. Yes, the Cartesian product is denoted by cross X. So this is the notation X this is X is a notation for the Cartesian product. And yes, you can see this example here. We have two relation, that is A1 and A2 relation, and in A1 relation we have two tuples, and even A2 we have three tuples. According to the Cartesian product, all the rows of A1 will be combined with all the tuples of A2. So my final resultant output will be nothing but 3 into 2, that is 6 rows. And also you can see here the columns, the columns will be added up here. You can see there are 4 columns here. So this Cartesian product is nothing but the combination of all the tuples of A1 with all the tuples of A2. Yes, the join operation is very important operations, where the join operation is denoted by, this is a notation for the join operation, and it is used to combine related tuples from two relation into a single longer tuples. So this is the general syntax of the join operation. So our join operations with the join condition, you need to specify in the join condition. Now the question is, what is the difference between the join operation and the Cartesian product? In join, only combinations of tuples satisfying the join condition appear in the result, whereas in the Cartesian product, all combination of tuples are included in the result. Let us look into, let us explain the join operation in a simple example. Here we have project number, project name, and department number is the attribute of project table, and in department we have department number and dname as the attribute of department table. Now when you join, the join condition will be using is department number and d number. And here you can see here, whenever you join two tables, at least one attribute should be the primary key. So here we'll be using department number and d number as a join condition. You can see here department and project we have joined by making of this notation, and the join condition is department number is equal to d number. So this department number belongs to department and d number belongs to the project, and the resultant output will have five attributes, 5 columns and 4 rows. You can see here department number and d number both are equal. So this is about the join operation. Let us understand the relational algebraic expression with a simple query of a company database. Retrieve the name and address of all employees who work for the research department. So I need to retrieve the name the name and the address of all the employees who work for the research department. So this research is nothing but the department name. So first what I have to do here is, I need, yes, I need both the relations. I need to join both the relations. So before joining both the relation, I need to retrieve those rows where department name is equal to research. The first I will retrieve those name where department name is equal to research. So department, again, to select the tuples, I need to make use of a select operation. That is sigma. The notation is sigma. Department name is equal to research, and the resultant output I am naming it as research underscore department. Now, so this research underscore department consists of those department with the name only research. Okay, now this has to be merged, this has to be joined with the employee, and the join condition I can specify here is department number and d number. So yes, I have joining research underscore department with employee, and this is the notation of the join notation, and the condition used is d number is equal, department number is equal to d number, and again the resultant output will be as represented as research underscore employees. Now I need to retrieve the name and address from research underscore employees. Yes, from research underscore employees I will be retrieving the first name, last name and the address, and ultimately finally my resultant output is this. This is how you can split the entire relational algebra into intermediate. Yes, that's it. uh, yes, we'll consider one more example. Yes, for every project located in Stafford, so list the project number, the controlling department number, and the department manager's last name, address, and birth date. Yes, for every project located in Stafford. Yes, this is a project location where this is a attribute where the Stafford will be available. Yes, list the project number. I need to list the project number. The controlling department, yes, I need to represent the controlling department number and the department's manager's last name, but the information of the manager it's in the department table, so I need to, yes, manager's last name. So information of the manager is over here, but the name of those employees is in an employee table. The name of the employee is in employee table, information about the manager is in department table, and the information about the project is in a project table. So I need to join employee, department and project. All the three tables or relations I need to join. I need to combine it. Yes, first from the project, retrieve those row where the project location is Stafford using the sigma operation, and name it as Stafford project. And from this, what I'm going to do is I'll be combining this Stafford underscore projects with the department, so that I get the manager's information. So I just combining it. Again, the join condition, as I said, the join condition should be at least any one of the attributes should be a primary key. Yes, department number here is a primary key, so that is a join condition. We have joined the two relations, and I have named it as control departments. Now from the control department, again I need to combine it with the employee, because I want the name, because name information is available in an employee table. Yes, control department and the employees combined, and the join condition used is manager SSN is equal to SSN. Yes, because I want the information about the manager, so I have used those attribute manager SSN is equal to SSN. And yes, ultimately from the project and underscore department underscore managers, I want to retrieve certain columns. Let's see which column I want to retrieve. Project number, department number, last name, address, birth date as specified in the question. I need to list the project number, the controlling department number, the department manager's the last name, address and the birth date. So this is how we retrieve using the pi operation. This pi operation will retrieve only the column. Yes, that's it about this query. Thank you so much. Thank you for watching this video. Please do like, subscribe and share.